Alright, so yeah, today is April the 3rd, and the states that I live in now have over 10,000 confirmed cases. It's becoming quite scary. I guess in the past 2 weeks, I only be out twice for grocery shoppings. Yeah, it's just trying to avoid the virus at all cost. Because I live with my wife and kids, I really don't want to endanger them. Anyway, so today is the third day of the April quarantine coding challenges. Today's question is also an easy one. If you don't consider this follow-up, the question is the maximum subarray. We are given an integer array nums. We need to find the continuous subarray containing at least one number, which has the highest sum, and return this sum number. So the example here we have -2, 1, -3, 4, -1, 2, 1, -5, 4. The subarray that contains the largest sum is this one, 4 -1, 2, 1. So this one here, it has a largest sum of 6. So by subarray we mean a slice of the array, and we couldn't skip elements within this slice. So it has to be a whole chunk of the slice of the original array, and we want such a slice that it will return the maximum. It will sum up to the maximum sum, a possible sum. And ideally, we would do a linear time complexity solution. And just for today, I wouldn't worry about this divide and conquer follow-ups. We'll save it for some later time. So basically, the solution for this question is to do greedy, kind of a greedy approach. So we just keep track of running window sum, and when we see a next number, we try to compare that number with the current sliding window sum. If that single number is higher than the current sliding window sum, which in this case -2, and we find 1, so that the running window is -2. When we find 1, we can discard the previous running window, because that single number defeats the whole previous subarray. And then the running window grows. We find -3, but we have to take it. So the running window sum become -2, and then we find 4, so we can discard anything that's coming before 4. Then we just take 4. The sum become, as we expand the window, the sum becomes 3, 5, 6, and then we will never see a single number that outperforms this window with sum 6. So that's the one that we're returning. So this will be the linear time solution. Just greedily have a sliding window, have a window, and whenever we see a single number that defeats the whole previous window, we just reset the window. So that's the solution, and we use a variable to keep track of the maximum window sum that we're seeing throughout this process. So that's the basically the process, the algorithm, and the time complexity is order of n, and the space is constant. So let's code this thing up. We're gonna have a window sum, which initially in the beginning it's just the very first number there. And we will have a variable that we will return. That's the maximum sum, and in the beginning it's equal to this window sum. So after this initialization, we will go through the numbers from the second location, of course, because this one is already in there. I is less than the size. We increment I after each iteration. what we're gonna do is try to grab the number at the location I, and or just if this number is larger than the previous window sum, we just restart the window. So that's just taking the maximum between the window sum and this number. After we updated the window sum, we also updated the maximum sum. And in the end, we just return the maximum sum. So I'm not blocking anything, right? Yeah. Okay. So that's pretty much the solution for the brief, straightforward order linear time solution. Okay, got something wrong here. What's the problem? Okay. Okay, so the problem is here. We need to increment this window sum with this number. So we are looking at whether we expand the window to include the new number, or if the new number by itself is bigger than the previous window. So that's the window sum update. Okay, yeah, this time it works. All right, I'll go back to the regular selected question after this one.